Are you ready?
Good.
Going. Okay, I'm going to start with a quiz. Today's quiz is a no talking quiz. So you can't talk to each other. It's your own private quiz. You can see if your vote is going up there. So here's what I'm going to do. I'm going to do an experiment, and you are going to tell me the result of the experiment before I do the experiment. Now, I've actually never done this experiment before. Yet. I didn't practice it yet. So we're going to find out what the result of the experiment is. Now, you should know I have a long history of experiments coming out backwards from the way I think they're going to go. When I've missed lecture this semester and last semester is sometimes because I give a seminar at other universities. And the seminar I've been giving you recently is how experiments that I thought would work out one way worked out exactly the opposite. Okay, so that's the forewarning. But I can't be misleading you one way or another because I haven't done this experiment, so I don't know if it's going to screw up or not. Okay, so here's the experiment. I'm going to take this pendulum, and I am going to swing it, and we're going to measure how fast it swings. Now, what do we mean by how fast? Do you see it better here, or do you see it better against the wood? Against the wood? Would it be better over here, maybe? Better or worse? Better. Okay, so here's our experiment. We're going to swing this thing back and forth. And we talk about how fast it swings. We're not talking about the velocity it swings. We're talking about the frequency, not even the angular velocity. We're talking about the frequency, or the reciprocal of the period. And we believe that that period is almost independent of the amplitude for small amplitudes. That was Galileo's discovery, and that's how come clocks use pendulums to keep time. If the amplitude gets long, it starts to take longer, which we figured out intuitively because the time would go to infinity as the amplitude gets up to pi. So if the amplitude is big like this, the period of oscillation is very long. Okay. I told you I didn't practice. Anyway, if we get up to here, the period's a little bit longer, not much longer. Just a little bit longer. It doesn't depend a lot on amplitude. Okay, stopwatch, people. So I'm going to go 1, 2, 3, go. You start your stopwatch when I hit go, and then when I hit 10, you hit stop. Okay? So, and you'll understand how it works. 1, 2, 3, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay. Now, what do we get for, I want to hear some numbers. What did you say, 12.8? Another number? 13.1. 13.1. Another number? 13.07. 13.07. Okay, I'm going to call that, 12.8 is a little suspicious. I'm going to call this a period of 1.3 seconds.
Wait, how much means
What do you think? Or I could call that an outlier. Let's work with this. Okay, so the frequency, not the angular frequency, but the frequency in terms of oscillations per second is 1 over 1.3. The angular frequency is 2 pi times that. Okay, now I am going to take this thing. Where'd it go? This thing. I'm going to find its center of mass. How do I find its center of mass? I balance it like this. And oddly enough, the center of mass is right on the number 12. I don't know why that is. Okay. Then I'm going to take this weight here, which happens to be 193 grams. This is 195. They're almost the same. And I'm going to put it right on top of this. And actually, if you want to see that the center of mass comes out in the same place, I'll mark where the center of mass is compared to the edge here. There's the center of mass. And then because I'm covering up the mark on this thing, I tape this down. And now there's this thing with the mass on it. Let's see where the center of mass is now. It's right where my finger is, right there. Have I moved the center of mass? I have not. Okay? Now I'm going to take this and swing it, and we're going to see how fast it goes. Now, no talking. When I do this experiment, does it swing faster or slower? Faster would mean that time is less. Okay? No, you're not allowed to watch it. You're going to go faster or slower, and this is the quiz. So the quiz is 1 is faster than 2. B, 1 is slower than. C, equal to. Cannot be determined. I have no idea. No talking. No talking. What? Do you want to hide that so you don't see it? Screw up the whole experiment. I should change the numbers around, change the question. Okay, you have 10 seconds left to vote. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You guys in the back. Come forward. Last 5 rows. Clear out, please. Okay, we lock up the vote. Now, another version of this question is, did you come to class on Tuesday? Okay, so let's try it out. Now, I didn't do this experiment, so it could mess up. It could be the theory is all wrong. Okay, are you ready? It's going to be 1, 2, 3, go, and then we count to 10. 1, 2, 3, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? What'd you get? 11.9. Other numbers? What? Other numbers?
12.
12. Other numbers? 12? That's all you have? What kind of stopwatch is that?
12.0.
What? 12.0, yes. 12.1. And that gives us, so we'll call this T1, and we'll call this T2, is 1.2 seconds, and 1.2 seconds is less than 1.3 seconds. Okay, so a victory for theory. Now, how are you supposed to think about this intuitively? If we go back and think about the simple pendulum, this is not the simple pendulum, nor was it without the tape the simple pendulum. I'm going to take away this mass, so you just have to remember it. You know the thing they do on TV, boxers, what are they, what am I talking about? You do these questions if you know, like the same kind of person. You go red, blue, blah, blah, and they say red, box, what are the kinds of underwear, boxers, and the other kind, briefs, boxers, briefs. They say box. You've seen this thing on TV, right? It's like a standard bar scene. What do people like? You have this dual questions. Anyway, the one I haven't seen is duct tape zip ties. Duct tape zip ties. Duct tape, zip ties. I don't know. I'm a zip ties guy. I can't stand duct tape, actually. Okay, so the thing is if this thing, and you can take duct tape off. I showed my 12-year-old nephew zip ties, and I told him that you could use them as handcuffs, and he tried it on his brother, and then couldn't get it off. Okay, so here's this thing swinging back and forth. Whereas if I take the point mass pendulum and swing it back and forth, you'll see that it swings faster, right? So why does this thing swing slower than that thing? One way to think about it, well, you can do all the calculations I showed last class, or you could say, what's driving this? What's driving this is the center of mass, gravity, and that's the same as what's driving this. What's resisting the motion in this case is the inertia of this thing, but this has two kinds of inertia. It has the MA kind of inertia, and it also has this I alpha kind of inertia. Or if you want to think about it energetically, the work that goes in of gravity has to go two places. It has to go into the kinetic energy of translation and the kinetic energy of rotation. And if you don't like that explanation for why this is slower than putting this right in the middle, then you can do the whole calculation I did last class. So James pointed out that last class I either made an error or I was unclear or he didn't catch it, so you might not catch it. I intended to call this distance L and this distance down here L, and with this is equal to 2L. So sometimes I was doing arithmetic with L's, and I meant for these two L's to be different, and maybe I messed up. I don't know. James, at least James, when he watched it, couldn't keep track of that. But I meant to be comparing this point mass pendulum with this pendulum. Okay, any questions about this example? Yes?
I kind of thought of it as like a frequency equals the square root of k over m.
Yes.
So with a higher mass than the frequency, I know since it doesn't get very square.
It's hard to do the k over m thing, and the reason why is for these pendulums, there's a k, which is proportional to mass, and an m, which is proportional to mass. So the driving term is also proportional to mass. So when I add this mass, it's got a bigger driving term, so it's got a big, if you want to think of it as being an effective spring, it's a bigger spring also. And if I put two of these next to each other, that'd be a bigger mass and a bigger spring, and they'd have the same frequency. Right, so I think it might be hard to do it with that k over m way of thinking. Any other questions? Okay, so let me just do a little digression on theory. So the basic theory that we have for the equations of mechanics is we have linear momentum balance and angular momentum balance. So let's look at linear momentum balance. For one particle, we have that F is equal to ma. And then for a whole collection, we have that the sum of the forces, all the forces on the particles, is the sum of all of the masses times all the accelerations. It's hard not to be true, because if it's true for each particle, we can add it up for all the particles. The big step in the logic, that projector is on. Anybody know this theory and want to figure out how to turn off that projector while I do this theory? Like Luke? Where's Luke when we need him? Okay. The big step in the reasoning in the laws of mechanics, and it's a subtle big step, is to replace all of the forces with all of the external forces. And this is equal to sum of the masses times the accelerations. And what do we mean by that is that that projector is on. And I like, those bulbs cost like $500, and it bothers me to have that money wasted. So I'd rather waste their time talking about it. Okay. So what's the difference between these total forces and the external forces is the internal forces. So what we make the assumption is that the internal forces cancel. And another way to state that is that the sum of the forces internal is equal to 0. So it seems obvious enough, especially if you think of all the particles obeying the principle of action and reaction. But if you think of all the particles as being atoms and obeying the laws of quantum mechanics, and they're actually interacting through electron fields and so on, it's not so clear that this is true, but this is an assumption that works out to be true. So for each particle, F equals ma. For the collection, this has to be true by adding up. Then we add the assumption that the internal forces cancel. The sum of the forces internal cancel. This then turns into the sum of the external forces, because the force on one particle has to do with the forces from the other particles in the system plus the ones on the outside. The ones on the inside we say in total cancel, and this is what we're left with. And then we have this simple theorem, which is easy to show algebraically. It's in the book. You should be able to do it yourself. That this turns into the force total is equal to the mass total times the acceleration of the center of mass. So for any system, no matter how complicated it is, linear momentum balance just turns into F equals ma. And you can go on in your understanding and misunderstanding of angular momentum balance. And this seminar that I've been giving when I skip class here about my experiments that mess up are about angular momentum balance. And I've managed, I think, to convince that most professors and so on that I talk to that they don't really understand angular momentum either. You can write equations, but it's a subtle business. But at least what I'm about to tell you, I hope you can understand. So how does it work? Is that for one particle, we have F equals ma. For one particle, and if you take the cross product of that as the position of the particle relative to some point C, certainly this has to be true also. So that's angular momentum balance relative to point C for one particle. It just has to be true. It's a theorem, in this case, that angular momentum balance follows from linear momentum balance, just by taking the cross product of both sides. Now for a collection, we get a theorem too, which is that we add up all of the positions of all of the forces relative to point C. And I'm going to call these J, because these are all the forces, which may not be coinciding with all the particles. And this is equal to the sum over all the particles of their positions relative to C crossed with their masses. Sorry, their masses times their accelerations. And this is all forces. And this is now a theorem also, but it's not a very useful theorem because this has all the forces, which means for each particle we've got to add up the forces from the outside plus all the interaction forces. So if we were looking at some object like this, we'd have to add up the Avogadro's number squared interaction forces between the atoms in the system. So now we make the same assumption that we make over here, that the internal forces cancel. So we assume that the internal forces cancel. And what do we mean by cancel in this case? Is we assume that if we add up over all the internal forces, Ri, this is J, relative to C, cross with this F, J internal, that this adds up to 0. What's that saying? Is the sum of moments of all of the internal forces on all the particles add to 0. That the internal forces are in static equilibrium. And then this tells us that the sum of all of the torques on the system, Rj with respect to C crossed with Fj external, is equal to this sum of Ri with respect to C crossed Miai. Okay. So this is the thing we use. It only follows from linear momentum balance when you add the assumption that the internal forces have no net moment. Okay, but this is our general principle of angular momentum balance, which applies to any system. And we can write this in a continuum form. So the continuum form of angular momentum balance is that the sum of all the moments relative to some point C is equal to the integral of all of the positions relative to C crossed with all of the accelerations added up over all the bits of mass. And usually the continuum version is easier to think about than the particle version, especially when you're dealing with objects that look like this, and you think of them as smooth and you blur out the atoms. You don't want to think about adding up over all the atoms. It's easier to think of this as a continuum. Okay, now this thing looks like a simple formula, but it's not a simple formula because all the different particles can have all different accelerations. So there are various simplifying cases. The main simplifying case in this course is that the system you're going to look at is a rigid object. Or it's a collection of a few rigid objects, and for each of them we can use the simplifying formula. So if we have this simplification, so this is what we're going to call H dot relative to C. So special examples are a particle. And for a particle, H dot relative to C is just the position of the particle relative to C crossed with the mass times acceleration. That was easy. That's where we started. And you can see that this formula collapses to this formula because for a particle there's no extended mass. The acceleration of the particle is the acceleration of the particle. These come out of the integral. The integral of dm is just the mass. The main example we're using for the rest of this course is a 2D rigid object. And for a 2D rigid object, this h dot relative to c is equal to the position of the object. And what do we mean by the position of the object? We mean the position of the center of mass of the object relative to c crossed with the total mass of the object times the acceleration of the center of mass. And this is the absolute acceleration. AG means the acceleration of g relative to some fixed reference frame or relative to some fixed origin with a non-rotating coordinate system. And then we add to this this I, G, omega dot K. So how do you think about this? You think of it as the particle is the motion of the center of mass plus this rotation term, which is the motion relative to the center of mass. So it turns out that for linear momentum and angular momentum and energy, you can think of, for any system, the linear momentum as that associated with the motion of the center of mass plus the motion relative to the center of mass, which is 0 in the case of linear momentum. You can think of the angular momentum as the angular momentum associated with the motion of the center of mass, which is, think of there being a particle at the center of mass. So as this moves around in crazy ways, we can calculate the angular momentum by thinking of there being a particle here, plus a motion, which is this I alpha term, which is the one you're used to from physics, from things which are rotating and not rotating and translating. And the same goes for energy. It turns out that the kinetic energy of this is the kinetic energy associated with translation plus the kinetic energy associated with rotation. Now, some people are whispering to each other. Do you want to ask out loud? Yes?
What was that symbol there? AG equals
This thing?
Yes.
This is a script F, and I use script F to represent a reference frame or a reference object which is not moving. F for fixed means the motion relative to a coordinate system. What coordinate system? One where the laws of mechanics are true. It's a self-referential definition. But we believe such reference systems exist, and in particular for most of mechanical engineering purposes, you use coordinates which are fixed to the furniture and the floor and the rocks and things like that. Other questions or comments? Okay, so I said this last class, but let me just say it again this time, so just to firm up the idea. Let me just do the pendulum example again, using this form of angular momentum balance. So here's the example, pendulum. So we're going to do exactly the same example. Most of the geometry and so on is going to stay the same. We've got this distance L, which is not the total length of the thing. This thing is going to have some mass m. We'll have g pointed down like this. We'll pick an x coordinate like this and a y coordinate like this. Associated with these, we have unit vectors in the I direction and the j direction. We could use polar coordinates for this thing. So we could have associated with this a moving coordinates, which has an ER and an E theta. And we want to then draw a free body diagram of this before we can use angular momentum balance. And the free body diagram has an mg here, and it has an ROX here. I don't even have to put O because there's only one of them, and an RY here. Okay, any questions about the setup of this problem so far? Towards the end of getting the equations of motion, as opposed to finding those reaction forces, we try to do this, what I call the American way, which is you take the things you don't know and you don't care about and you kill them. So what are things we don't know and care about? we don't care about these reaction forces, and we can kill them by taking angular momentum balance about this point O here. So if we use angular momentum balance relative to point O, this turns into the sum of moments relative to O equals h dot relative to O, rate of change of angular momentum relative to point O. So what do we have for this? On the left-hand side, we have the moment of this force, which is just this force times this lever arm, which is little l sine theta, and that's in the minus k direction. So we have minus l sine theta k. And then on the right-hand side, now let's use our new way of evaluating this. We have the position of g relative to O crossed with the acceleration of g times the total mass plus ig alpha or omega dot k. So this is this general formula which we're going to say, now how general is this? It's not super general. It's the formula that works for rigid objects moving in general ways in 2 dimensions. So in order to evaluate that thing, we have to look at the various quantities. What is Rg relative to O? Well, let's just call that L times E sub R. What's the acceleration of G? Well, that's an L theta double dot multiplied by E sub theta minus L theta dot squared E sub R. Or we could have used our cross product formulas for calculating this. We could have said this was omega dot k crossed with the position of g with respect to O plus or minus omega squared r of g with respect to O. This thing is equivalent to that thing. We can calculate it either way in this problem. Now we want to use this over here. So we have our equation of motion minus L sine theta k is equal to, and then we have our r. The easiest way to write that is as L E sub r. And then we have that crossed with the acceleration, and we copy down this thing, which is the simplified version of this thing, which is L theta double dot E sub theta minus L theta dot squared E sub r. This thing gets multiplied by the mass, and then we have plus theta double dot I G K. Why don't you just copy that down and ask me questions before I just finish up the algebra? Yes?
On the left side of here,
MG would be a good thing to have over here. And it would be nice to have an MG over here too. Any other errors or questions? And thank you for asking that in an honest way. Professor Ruino, why did you leave out MG? And I have to tell you again that I'm senile. Okay, so, yes? This quantity here is the acceleration relative to the fixed frame. Are you having trouble? Is this bothering you? So I guess one confusion is the difference between a coordinate system and a reference frame. Who asked the question? I just want to make eye contact here. So you're seeing here ER and E theta, and you're saying that's not the fixed frame, that's the rotating frame. Is that your confusion? Okay. My claim is that this is the acceleration relative to a fixed coordinate system. I am using this rotating coordinate system to represent that vector. This vector for the acceleration is going to change with time. So the absolute acceleration of this point here has 2 parts. A tangential part along the circle, the theta double dot part, and a radial part. And I use these coordinates, these unit vectors, to describe that vector as the sum of vectors in these 2 directions. When this gets to another position, it also has an acceleration that's tangential and radial, and those tangential and radial directions have changed. So the coordinate system I'm using, the unit vectors I'm using are rotating, but the acceleration I'm calculating is relative to the fixed frame. If I were calculating the acceleration of this thing relative to this frame, the meaning of that would be I get on board that frame, I'm on the spaceship, I close the windows, I look around, and using a coordinate system that's moving with it, I see how much are things moving, and I don't see any motion at all. So if I was looking at the acceleration relative to the body, I would have zero acceleration. That's the thing about a rigid body. A rigid object is none of the parts move relative to each other. It's a confusing thing. So we're looking at the acceleration relative to the fixed frame, but we're representing it in a coordinate system which is changing in time. Was that what your confusion was about?
Yeah, I guess it makes more sense we have
We could at any instant in time write ER and E theta in terms of I and J. It's just that everything would look more complicated still. Okay, so now we want to simplify this formula. We have on the left minus mgl sine theta k, and on the right we have a cross product. Part of the cross product is 0 because ER crossed ER is 0. The only thing that contributes to the rate of change of angular momentum of this point as it moves around is this acceleration, not this one. This one makes no contribution to the rate of change of angular acceleration because it's along this line that we're going to cross with. So the second term drops out. ER crossed with E theta is k. So this term turns into L squared k. So we have an L squared, and we have an m, and we have a plus ig, and these two together go with a theta double dot k. Then we can take this whole expression. Since both sides are in the same direction, the scalars which multiply have to be equal, but if we want to be formal about it, we take the dot product of both sides with k, and it tells us then that theta double dot is equal to minus mgl sine theta over ig plus ml squared, as before. Okay, so we get back the same equation of motion, and from this we can stick it into MATLAB. If we're really good at math and we like elliptic integrals and so on, we can try to write the formula for it, but the formula doesn't tell us anything that MATLAB doesn't tell us anyway. So we can figure out the motion of this pendulum, and you could stare at your computer screen and watch your computer screen do the same thing. Okay. Anybody have doubts about their ability to go from this problem statement? In fact, just from looking at me here, could you go from this and say, please, I say to you, please simulate this in MATLAB, could you do it? With the picture and everything. And if you could not, what is it that you're insecure about? Yes?
I'm really still not really clear how to animate something.
You're not clear how to animate something. Let's see, did you watch the video of my showing you how to animate something? Is there anybody who watched that video and looked at that code, and after that you still don't know how to animate something? If there is such a person, I'll go over it again in lecture. Okay? Or send me an email if you were too shy to ask right now. Anything else you'd be insecure about? Okay, now this derivation looks a little more complicated than the one I did last class. Remember the last class, on the right-hand side, I just quickly jumped over to this thing being equal to I0 omega dot k. And that's how things work out if you have one fixed point. So for this problem, the calculation I just showed you is a little longer. The issue is, somebody said, well, why aren't we using this all the time, or are we going to use this all this time? Is that this formula, this one, for h dot, only works if you have one point on the object which is fixed in space. And in general, we want to look at more complicated motions. So for example, let's say I take a square like this, and let's leave gravity out. So I'm going to have a square with no gravity. And I'm going to pick some reference frame over here, I and J, and I'll put an O here. And to show you that I mean for this thing to be fixed in space, I'll say that's the fixed reference frame, which means that's not going to move. Measuring motion relative to that, we get things which work out right with Newton's laws. And we're going to take the square which is sitting here in space. It's got some center of mass. It's got some mass. It's got some moment of inertia about the center of mass. And we're going to apply a force to it. And it's going to be a constant force. F is going to be equal to F0I. So I'm going to keep this force constant. Now I'd like to ask you a question, which is, if I start this from rest, how does this thing move? So if you want to picture it, you're in space, and there's a block, and there's a constant force suddenly applied to the still block. If you want to make it a problem you could do sort of in the lab, imagine you have these air hockey tables. Anybody not know what an air hockey table is? So you have an air hockey table, you put a square block on it. At one corner you tie a thread, and you pull on that thread, always careful to keep the force constant and the direction of the force constant in the room frame. How does this thing move?
You're keeping the force applied to that corner no matter where that corner is, right?
I'm going to always apply this force to this corner no matter where this corner is, and I'm always going to keep that corner, I'm always going to keep the force constant, I'm always going to apply to the corner, yes. So how does that thing move? Yes?
So motors initially rotate, but after it gets to...
Did I ask you? I was asking them. Yes? What? You're going to answering my question? Okay, I don't know if I was ready for you to answer my question. I want you to understand the question first. Now let's go for answering the question. Now you ready to answer the question? Okay. Let's answer the question like this. We'd like to keep track of the motion of this thing here. And how does this thing move? Does it move in an oscillatory way or not? Okay, so the answer, what we want to look for is like this or not. And I'd like you to vote with your clicker. Do I have to do anything?
Yeah.
How's that? Now vote with your clicker. Is the question clear?
What is it you're asking?
I'm asking, this is starting from rest, and I'm going to suddenly apply this force, a constant force always applied to this point here, and I want to know how this is going to move in time. When I track the center of mass, does it move in some kind of oscillatory way or not? Vaguely like that picture there or not? Okay, 5 seconds left. 4, 3, 2, 1. Only 99 votes. One more person. Come on, one more person vote. 99, 99, 99. Going once, going twice. Can't even get 100 votes here. Okay. B says not. Okay. Let me give you some satisfaction here. B. Not.
Yay, you didn't trick us.
I don't know whether I tricked you or not. I think I could have got you to... I tricked some people, I guess. Okay, so what's the right answer? Raise your hand, somebody. Somebody who said not. What do you want it to be? What do you want?
Straight line.
A straight line. How do we see this from what's on the blackboard? If you look at any system, the total force gives you the mass times the acceleration of the center of mass. This equation is correct for any system. In this system, the center of mass is the center of the square. The force is a constant. We're starting with zero velocity. So this is as if we applied the force to the center of mass. So if you want to know the center of mass motion of this system, it's exactly the same as if we'd applied the force to the center of mass. Okay, so this is the right answer. And the center of mass motion, if we want to write it in vector form, the center of mass is a function of time. If this starts from rest, the center of mass motion of this thing is F0 divided by m multiplied by t squared divided by 2 in the I direction. This is the position of the center of mass as a function of time for this problem. Okay. Now, there's something oscillatory in this problem. What's oscillatory in this problem is that this thing's going to swing in circles. Now, does anybody have an idea about how this thing oscillates? Anybody have a kind of definite idea about how this oscillates? So they can say something sort of precise about it. This point goes in a circle relative to this point because all pairs of points on rigid objects go in circles relative to each other. But this point is going to the right. So this point is going to the right. This point is moving in a circle around it. But how is it moving in a circle around it? Yes? Go ahead.
Okay, won't it just initially sort of rotate and then eventually just winds up going towards the right and stuff?
No, it won't do that. Yes?
Will it rotate through 270 degrees and rotate back?
Yes. It will rotate through 270 degrees and then rotate back and then rotate back and then rotate back. And what equations will it be following when it does that rotation? So this problem, in disguise, is this problem. This is a pendulum problem, again, rotated sideways. It's different from the pendulum in that the driving force doesn't act on the center of mass. It's just a driving force here. But if we take angular momentum balance relative to point C, and we measure the motion of this thing as an angle relative to this one, angular momentum balance relative to point G, then we have the acceleration of this point relative to this one, plus this I alpha term. All we have is the I alpha term. And we get this force here, which has a lever arm depending on this angle. So we have, as a torque on this system, we have this force 0 times the length of this thing. So let's call this half length d. So the length of this thing is the square root of 2 times d. And then we multiply this by the sine of theta. And this torque balances the angular acceleration, which is this ig theta double dot. And then we have to have a minus sign here. So we get back exactly the pendulum equation again. And I skipped the algebra. I did this kind of in my head. I'm not asking that you should be able to do it in your head like that, but this is how it works out. So this follows the pendulum equation. It just oscillates back and forth exactly according to the same differential equation with different constants that we've dealt with before. Okay. Isn't that a soothing sound? Or gross sound. I don't know which one. Any questions while we wait for the blackboard to dry? Philosophical questions, technical questions. I'm about 1 for 4 in this game. There you go, 2 for 5. I was in Ohio State for the Ohio State basketball game when they lost to Kentucky, and I watched it in a bar. It was very depressing. Okay. They weren't as good as me on average. No questions. Okay, let's take an example. Let's say I have a bar which is held by 2 springs, and they have some K like this, and here we've got some G, and we've got some L like this. And here it is in equilibrium, hanging like this. And then what we're going to do is we're going to cut this thing, and we want to know what is the first motion after the cut. So what do we mean by what's the first motion? Well, we want to figure out, say, what is the acceleration of g, what is the angular acceleration, and so on of this thing. So we're going to cut this thing. How does this thing look before the cut? And how does it look just after the cut? So we have free body diagrams before and after. Before the cut, we've got mg like this, and this is in static equilibrium. So these 2 spring tensions are mg over 2 and mg over 2. And just after the cut, well, what happens just after the cut? Gravity doesn't go anywhere. This force goes to 0 because we've cut that spring. What about the one on the left? What does that force turn into immediately after the cut? Well, what happens is if you suddenly change the forces on a system, it suddenly changes the accelerations. And that suddenly changes the rate of change of velocity, but it does not suddenly change the velocity, and it does not suddenly change the position. So when you make a sudden change in terms of suddenly changing the force, the configuration, the shape, the position, the angles do not change. And that force on the left-hand side is the stretch in that spring. But the stretch in that spring doesn't change because there's no sudden motion. This point might suddenly have some acceleration, but it doesn't suddenly have some displacement. So immediately after the cut, and that's just after, this force is still mg over 2. And this one is not mg over 2. Professor Arena, why is that mg over 2? Because of senile again, it's mg. Okay, so how do we figure out the motion of this thing? So just after the cut, what's the acceleration of g? It's equal to mg minus mg over 2 divided by the total mass multiplied by minus j. So linear momentum balance tells us in one shot that right after the cut, this thing goes down like this. Now what does angular momentum balance tell us? In this case, the easiest angular momentum balance equation to use is the one about the center of mass. And by the way, if you have no inspiration and you don't know what else to do, use angular momentum balance about the center of mass. You can always take angular momentum balance about any point you want. The advantage of using angular momentum balance about the center of mass is that r cross ma term doesn't show up, because r, the center of mass, relative to the center of mass, is 0. So this tells us that the sum of moments relative to the center of mass is equal to h dot relative to the center of mass. What is the sum of moments relative to the center of mass? It's L over 2 times mg over 2 and that's in the minus k direction. And what's the h dot relative to the center of mass? It's ig theta double dot k. So we get from this that theta double dot is equal to, and how are we going to measure theta? We'll measure theta in this counterclockwise direction. When in doubt, measure theta counterclockwise. So this gives us theta double dot is equal to minus LMG over 4 divided by IG. And that IG is something you know how to calculate. Okay, that's that example. Any questions about it? See you next Tuesday.